over. Multiply through by N1 over N2. So, what do I end up with here? What's this? Well, I have some torque. Minus sign means it's going to go the opposite direction, so I have an input torque going clockwise, J2 is going to go counterclockwise, is all that means. The torque equals something times acceleration. Well, what's that something?
Inertia?
Equivalent inertia. And notice it's the inertia of J1 times the ratio squared plus J2. Equivalent inertia. Almost look at this thing here. Those have this kind of gear ratio squared effect coming in. And so this inertia here, J1, as looked from the other side of the gear train, looks like that inertia times the gear ratio squared. Where do you see that principle?
Parallel axis.
What's that?
Parallel axis.
I'm thinking more as far as mechanical things. In fact, if you've ever seen the little toys, little cars, spinning across the floor, what's inside those? And if you had those, you'd take them apart. That's a little 5-wheel in here. So what's it doing? Well, that little 5-wheel, through the gear ratio, what's that called? Really big 5-wheel. Stores up a whole bunch of energy. But really, the mass of it is pretty low, so it's not the shoots across the floor. Right? It's also a problem in a lot of mechanical systems, such as, I say, hands and arms and things where we're trying to make things very small, so we can swing things longer, so it fits. We have this big gear ratio. Suddenly, this very small, light motor looks like what? Big, heavy, flat. It's what's called effective inertia. That can be a real problem. All right. We have, in this case, two inertias, two things that store energy. However, how many independent energy storage elements do we have? One. Explain everything is one equivalent energy storage element. Right? And it goes to, you guys did bond graphs, that's called the causal conflict. Right? And I have to take one of them away as being independent. So let's look at that in terms of the three links. I'm going to draw the graph of this. J is like masses, the reference is always ground. Has to be ground. Same rationale as mass. Right? The original frame of reference. All right? We have truck source on this side. Okay. And we have this gear train. The way I'm going to draw this gear train is it has two sides to it. It has, again, one side, and it has, again, two sides. Go out like that. So this is the gear. Called two-port system. source. What does that mean? Angular velocity. It means it'll provide the angular velocity. And then find it. Is there anything there that does that? No. Second thing goes in the tree. Things that store angular velocity, which are what? The inertias. Try to put those guys in the tree. And then, essentially, I should be, what, finished here, right? Because I've connected everything, caused no loops. Okay. What's that say? If these two inertias are in the tree, we're defining them to be each a state. So I say this is a second order system. We found that as first order. So, we have a problem here. And it's easily resolved, however. And that has to do with this transducer. Okay? So let's look at that transducer. All right, gears. It's converting an omega 1 to some other omega 2. And we convert some torques to some different torques. The good news is converting a cross variable to a cross variable, and it's converting the through variable to a through variable. This is what we call a transforming so it's converting the cross variable to the cross variable, and the through variable to the through variable. And bottom graphs that would be effort to effort, flow to flow. It's a transducer. Make sense? It is not converting, or really giving a ratio between omega to torque, or the torque to omega. Do you remember what those are called? Just a moment. Parity. Right? This is transducing. The rule for transducing system is one leg, one branch, is in the tree, and the other is in the wings. Results of causality. In bottom graph, remember you have what causality slash on one side, and then the opposite side. Right, the same thing. So we're doing exactly the same thing. That resolves the problem. It says one of these must be in the tree, one must be out of the tree. Well, one of these in the tree, let's say N1 in the tree, that says what? J1 has to be out of the tree. And how many states do we have now? One. And that state is velocity of J2, omega 2. Okay? That makes sense to you? Okay. We just adjusted the rule. Okay. And then it works very nicely. So let's solve this thing by putting graphs. More functions. Same thing. All right, so I'm going to take all my elements. Well, we'll put our primary variables. We have torque source. We have torque of J1. We have omega, I'll call it N1. Torque J2. And omega J2. Those are our primary variables. So they're the through variables, the things in the links. The cross variables are things in the tree. That's me. Of those which are states, source in every state, through variable of a cross storage element, not a state. These are transducer ones. They don't store energy, therefore not a state. This is the only one that counts for the energy. Omega J2 is the only state.
you draw the tree, but not just doing it on top of that other design, other diagram?
I can do that, so. This is change 1, and this is change 2. That part's the tree. The links, dash lines. Dash lines are the links.
Thank you.
Okay, so, let's look at all these. So, I'm going to write the elemental equations, and I'm not going to write for the source, so, let's write the elemental equations. So, in here we have Kirchhoff's voltage law, Kirchhoff's current law, substitute, and then get all the speed equations. So P of J1, the torque in the inertia is what? J1 times omega J1. Omega N2, N1, omega N1 is equal to what? That's a gear here. So it's going to be the relationship of omega 2. What's the relationship? N2 is equal to 1 minus, right? Torque of N2 is equal to what? Well, it's M2 over N1. Right, so those are the relationships we're here. And then the last one, omega J2 dot, 1 over J2 times T of J2. That's going to be our state equation. I know that's going to be the state equation because it's going to have a derivative from the result. All right, let's look at Kirchhoff's current and for voltage laws.
Question.
Yeah.
So you have like omega J1 and omega N1. Are those the same variables?
Omega J1 and omega J2.
Like in your first?
Sorry. Well, I'll just leave this. This is N2. Let's say here. So we're going to make those substitutions here in just a second. So just write in terms of the elements themselves. So what is omega J1 equal to? We use Kirchhoff's voltage law here. It's a good substitution here for omega of this right here. Well, in terms of the tree, where's the easy loop to do Kirchhoff's voltage law? Right here. Omega J1 is equal to omega N1. Right? You guys see that? They're going at the same speed. Omega N2. This one. That's equal to what? Omega J2. No, it's getting very good. T1. That's the torque in this branch here. Let's look at Kirchhoff's current law here. It's equal to what? Torque going in minus the torque of J1. T1 must be torque source minus torque J1. Kirchhoff's current law. And then torque in J2 is equal to minus the torque in N2. Okay, there's all of those. These per couple. Substitute. This is a no-brainer part, so be careful. Get everything right with the right signs. Okay, here's our state equation. So now we have to see, well, T of N2 is minus N2 1. T minus T1. Right. Maybe we should multiply that through. Make two errors. Minus N2 1 plus 2. Okay, I get that right. In T of J1, it's not a state variable, but up here I have it in terms of this one.